Okay, so it's my pleasure to introduce the speaker for today. Our speaker is Professor Sara Mouradian. She's an assistant professor in the ECE department at the University of Washington, Seattle. Professor Mouradian did her bachelor's and master's in engineering from MIT, and then she did her Ph.D. also at MIT in the quantum photonics group. And this is where Sara and I overlapped, spatially but not temporally. I did my postdoc there. And Sara actually was sort of a lab legend there. The reason why is that she, at the time, was one of the pioneers who developed nanophotonic devices in diamond, which is obviously a very important quantum material. And at the time, that was a very daunting challenge. Like, people didn't know how to do that. But she had a change of hearts when she became an IC fellow at UC Berkeley and decided to pursue a different quantum computing technology, which is arguably probably better, using trapped ions. And then she became a professor. I hope I didn't offend anyone. And then when she became a professor, she continued pursuing the same platform, trapped ions, for quantum computing, and this is what she will be presenting today. So thank you very much for coming. It's a pleasure, and welcome.
Thank you for the nice introduction. Yeah, so today I will be talking about the work that we do at my group. We are in the electrical and computer engineering department, as mentioned, and so we're looking at quantum technologies from a engineering point of view. And so we're looking to solve the device and system scale problems that are holding us back from creating fully scaled, useful quantum technologies. And today I'm going to talk about how we can increase the number of qubits and the connectivity between those qubits without sacrificing fidelity too much. Before I begin, I'd just like to thank the people who are actually doing the work. So this is a new and growing group at the University of Washington, and we are interested in new Ph.D. students. So if there are any undergrads here, which there may not be, feel free to reach out. And yeah. Okay, let's begin. So I'm not going to belabor this point because I think hopefully all of you are hyped enough about quantum technologies. But if we had a large-scale, controllable quantum system, we could do a lot of things. We could get provably secure communication. We could improve sensing, and I think atomic clocks are the best of these, example of this. Trapped ions actually have the best time uncertainty, and there's promise for quantum technologies to give us timekeeping even in GPS-denied locations. We could also build gate-based quantum computers that could, for instance, help break RSA encryption, and then we can also do quantum simulation either in a gate-based system or a analog quantum system, for instance, to simulate nitrogenase. So that's the molecule that I have there. It is one of the important building blocks or important components in grow-in food production. So if we could simulate how this works to better understand it, perhaps we could get more efficient food production and solve world hunger and save the world. But to do that, let's dig in a little bit to the resources that we need. So we would need, estimates show, about 100 million physical qubits and 10 to the 14th gates. And of course, these numbers are a bit hand-wavy and qualitative. They depend on what exact platform you're using, what your exact error rates are, what the exact encodings that you use. But this is to give you an idea of the order of magnitude. And we compare that to today's systems, where the best systems have on order 100 qubits and can do 100 gates. Right, and so this is orders of magnitude difference, and the general question that the whole field wants to answer is how are we going to bridge those 6 orders of magnitude in qubits or 12 orders of magnitude in the number of gates. And this is our daunting task. And then, of course, there's also theorists thinking about the opposite problem. How can we bring down those numbers to something a little bit more reasonable, or if there are problems that need less resources. So now I'm going to start talking about ions, but I'd like to say this is a fairly small group, so if anyone has questions at any point, definitely just raise your hand and ask. I'm happy to have this be a conversation. I don't need to get through all my slides. All right, so we in our group, as mentioned, we use trapped ions. In particular, we used singly ionized calcium-40 ions. These ions are great because we can trap them with only electric fields, DC and RF fields. We can also control their electronic state completely with only 4 lasers. So this is a simplified level diagram of calcium-40. We have the ground state, and we encode our quantum information between one state in the ground state S manifold and one state in the this D manifold. And this transition is a quadrupole transition. So if you remember from atomic physics, this transition is not allowed or only very weakly allowed. So this excited state lifetime is about 1 second. And so this gives us quite a long time to store our quantum information. We can also use the dipole transition, so we could scatter off of this transition to read the state. So if we're in the 0 state, we'll get a lot of scattering off of this transition, but if we're in the 1 state, we won't get any scattering at all, and this gives us very high fidelity and easy readout of our quantum state. And then 854 and 866 we use to repump everything and control the full state. But ions have a secret weapon that other quantum systems don't have, and this is their motional modes. If you trap a single ion in a harmonic electric potential, you can that ion will have motion, and we can break it down into 3 orthogonal motional modes, of the 3 cardinal directions. If we have 2 ions trapped in the same potential, then we will have 2 motional modes in each direction, so a total of 6 motional modes. And those 2 ions, one is the common motion or center of mass mode, where their coupling vectors are in the same direction, in the same magnitude. And the other is the stretch mode, where they're equal magnitude but opposite direction. And this will, I'll talk about this in detail later in the talk. And the beautiful thing about these modes is that they can be cooled to the ground state, and we can also coherently control their occupation. And finally, we can use them to mediate entanglement, because these motional modes are shared between all ions trapped in the same potential. So this allows us to kind of get this natural form of entanglement that gives us all-to-all connectivity between ions that are trapped in the same potential. So let's talk a little bit about the specifications of a trapped ion. So these are numbers for calcium ions in particular. Calcium ions, and these are state-of-the-art numbers. So calcium ions have hundreds of millisecond T2 coherence times, limited by magnetic fields and laser noise. Single qubit gates can be done in about a microsecond with 4 nines of fidelity. So about 1 microsecond, 4 nines of fidelity. 2 qubit gates are always the hardest, but we can do them in tens of microseconds with 3 nines of fidelity. And state preparation and measurement errors are incredibly low, with, again, 4 nines of fidelity. So all of these give us a very promising building block. But I'd also like to give you the more the numbers that you could expect from a random experiment. Because I will say that not all of these numbers were demonstrated in the same system, right? Sometimes you have to optimize for one thing and then other things fall off the side. And also, you can have an incredibly well-engineered system, and the question is that it's scalable. So I also wanted to give you an idea of what we're shooting for in our lab and what a kind of normal ion trap lab can get. So these are numbers that I got during my postdoc work and what we're hoping for in the lab that I am currently building. So we can get 10 milliseconds of coherence time, limited again by magnetic field noise. To get that extra order of magnitude, you'd have to build a mu metal shield to shield yourself from all stray magnetic fields. We can get, the single qubit gates are fairly easy. I would say that number is limited by cooling and also just how much patience we have to measure all those nines of fidelity. 2 qubit gates are the hard one, right? I think you can get hundreds of microseconds at 98% fidelity. That should be doable, but getting that extra few percent really becomes an exercise in patience. If any of you have worked in the lab, usually it's easy to get 90% of the way there, and that extra 10% is really what requires a lot of work. And again, state preparation and measurement, it's fairly easy. It usually takes longer, and this number is usually limited by our patience in measuring.
2 qubit gates, the color centers, you have to use these hyperfine mediate interactions and two qubit gates one at a time. In trapped ions, I'm guessing these are direct dipolar interactions.
Yeah, you can think of it like that. I think like it's through this motional mode. Yeah.
2 qubit to 3 qubit to 4 qubit gates, would the fidelities, how would they scale? For trapped ions, I'm guessing it's be more favorable because you can use the collective.
Yeah, so if you want to create just a fully entangled GHZ state of all of your ions, that's actually fairly straightforward. You just illuminate them all at once, and then you put it for the right amount of time to get the phase that you want between your whatever entangled state you want to create. Creating arbitrary entanglement is slightly more difficult, just because every entangling gate has some fidelity, and then you can stack as many of them as you want, but the overall system, the overall operation may be lower fidelity.
Will it be fidelities, will they multiply, or will they, it'll be better than that if you were to stack? Like, I'm trying to understand how the gates stack up.
Yeah, so one thing is that you can make any arbitrary entangled state by a sequence of single qubit rotations and control NOT gates, right? So that's one thing, and there the errors stack as one would expect. But there are, for particular entangled states, there are tricks that you can play, but there's been work done to understand how these many body interactions can be made general, but in general you can't be like, I want this arbitrary state, and I would know exactly which laser pulses to put onto the ions to make that.
So there's a compilation problem.
Yeah. Definitely, yeah. And actually a problem that I won't delve into a lot during this talk is parallel gates. So if you want to do a gate on 2 ions and also another 2 ions, that also is a problem. But I won't delve into that in this talk. I will be talking about some other errors in long ion chains, though, in a second. Okay, so now we have these amazing specifications, and now we just need to trap and control 10 to the 8th of them. So fine, we'll just copy and paste until we get it. So how do we trap, a few first? So we trap ions so if you remember from your electromagnetics class, you can't create a fully trapping potential, right? The only way to make a fully trapping potential for a positive charge is to put a negative charge there, or vice versa. So what we do is we play a trick. We use RF fields, and we make the polarity of this field move back and forth fast enough, so much faster than the motion of the ion. So the ion only sees the average of the field, and we are creating this 2D trapping pseudo-potential. And in the third dimension, like in and out of the planes, we can put a DC field to trap ions. So in this configuration, we'd have very strong trapping in the what we call radial or RF directions, and weak trapping in the axial direction, and so we get a string of ions coming out of the page. So this is called a Paul trap, won the Nobel Prize. It creates a really nice harmonic potential, so we can very easily make it into a quantum harmonic oscillator, which physicists love, but it is not scalable per se. But we can unfold this to make a planar geometry. So what we do here is we take the 2 RF electrodes and pull them down here, one ground plane, and then we imagine there's some other ground plane up at infinity, and we get a potential that looks like this. And you can still see a region here where you would get a trapping location. And it doesn't look quite as harmonic as it did before, but it's still, it turns out it's good enough, and you can still approximate it as a harmonic oscillator, and it's fine. There is some price you have to pay, but what you gain is ease of fabricability. So this is a surface trap that was fabricated in my group by a Ph.D. student, Hei Lim, where we have the RF electrodes in purple, the ground electrode in yellow, and then a series of DC voltages, or DC electrodes, which we can put varying voltages and actually have multiple different trapping locations. right? And so even with this simple structure, you know, a new lab can create a structure capable of trapping tens of ions in multiple different groupings. Okay. And by changing these voltages, you can change the strength of each trapping potential, where they are, et cetera. And you can shuttle ions between trapping potentials as well. And so this allows us to take advantage of microfabrication to create these complex electrode geometries. So, you know, our group and also many people in the field believe that trapped ion computing will be inherently modular, where each module corresponds to one set of ions trapped in a single potential, right? So we spend a lot of energy carefully engineering each module, or how many ions are in each potential. And in each module, right, we have this all-to-all connectivity, which means that we can do entangling gates on any arbitrary pair. And then we can also link different modules, either with optical links, which can be slow, they're probabilistic, but once you get a photon, it lasts for a long time, so they can give us very long distance links. We can also, but ions have this nice, because they're charged, we can grab them with electric fields and shuttle them around, and this gives us physical links. And so these are fairly fast. The speeds are defined by the trap frequency, but of course, you know, they're somewhat limited in distance. You can't go meters, you can kind of only go the distance of the chip. So those are two options that we have. And so, you know, the goal here and the idea is that if we spend a lot of time engineering both of those things, we can copy and paste these modules and increase the number of qubits without increasing the rate of errors too much. And I just want to belabor one point, which is what's nice about this is that within each module, you have all this connectivity, which is good. It gives you a lot of power in computation, but it also means that errors can propagate quite freely. Whereas in this, so if you had all of your ions in one fully connected system, you'd have a lot of pathways for your errors to propagate, and the full quantum state would be harder and harder to control. And this modular system also kind of gives you these bottlenecks, very controllable links, that allow you to stop the flow of errors. But it's a general question of what will this look like in the end, or, you know, the simplest form of this question is how many ions should I put in each module? Right, we have anywhere we could put 2 ions in each module and shuttle them around, or we could decide to put all 10 to the 8th ions in one potential. Yeah. Yeah.
Between the modules, what is the connection? Is that one-to-one or star connection possible? Or?
So the way that I would think about it is a single qubit that connects one single qubit in one with one single qubit in the other. So it's, yes.
You can choose which qubit?
Yes. Yeah, so you kind of split one off and then shuttle it over to, you could like split 2 off from 2 and then shuttle them together and then doing entangling gate. And, you know, then propagate entanglement between these two. Yeah.
This process is coherent?
This process is coherent, so you can keep the quantum state as you're shuttling it.
It's kind of difficult to imagine, like you're wrapping an ion physically and moving it,
Yeah,
and you're retaining the quantum state.
yeah,
So
and that's because
yeah.
it's in the electronic state and not the motional state,
Yeah.
right? And so there are a lot of errors that you incur. You know, there's going to be some magnetic field gradient probably, so you're going to pick up some phase, but that can be calibrated. So you say, okay, I know that every time I move from here to here, I pick up some phase. I just either keep track of that in my computer, or I could undo that phase. There's also going to be some motional noise, but this is the trade-off, right? So this is one of the points that goes into answering this question. How many ions, you know, I could trade number of ions for, you know, amount of links that I need. Mm-hmm.
Entanglement. Do with, so that also you could do, right, with optically active ions.
Yeah.
The way you would do it in say color centers.
100%, yeah. But that is A, probabilistic, and B, ions are really, the negative thing about ions, it's really hard to put them in a cavity. So there are people who have put them in cavities, but this is So Tracy Northrup was trying to start this when I was starting my Ph.D., and now they have done it. and they do it really well, but it's not like, it's even harder than putting NVs in a cavity, I would say. Electrically. So you can imagine putting, if you had an ion here, you could imagine putting moving voltages on these to kind of make a conveyor belt to move the trapping potential along this line here. So they call it the bucket brigade. You just like move your ions along. Yeah? Yeah, you can make them have coherent states. Yeah, I see. The electronic state and the motional state as well. But normally we care mostly about the electronic state. These are all great questions. Any other questions? Okay, so let's look at some solutions. So Quantinuum, which is one commercial trapped ion company that's spun out from Honeywell, has decided that the answer to this question is 2. Right, so they've taken the minimal answer, and they recently published this paper in May, I guess, about a racetrack trapped ion quantum processor, where these little yellow dots, if you can see them, are ions that are being excited or being computationally active, and these red ones are ions that are just memory qubits that are not at that moment in time being addressed, or their state is not being changed. And the idea is that they can move these ions around this racetrack, they can swap them around, and they can get arbitrary connectivity just by the shuttling. So here, and so this makes it easy because, for instance, their optical excitation, they don't have to worry about crosstalk. These ions get caught up, but these ions are 700 microns away from each other. So it's super easy to avoid any optical crosstalk. But then the price that they have to pay is that they have to do all these shuttling operations. So if you look at this paper, actually, I think on an average program, about 75% of the time is spent on shuttling operations. And actually, their leading source of error is due to these shuttling operations. But still, they have the current best operation of any trapped ion processor that has been published, right? So even with all of that, they still get the best results, and that's because some of their other errors can be so low. On the other hand, IonQ, which is another now publicly traded company, has decided, well, I don't know what their final answer is, but their current systems have about 32 to 50 ions in them. And so, so each trapped on something like this is made in Sandia National Labs, and they get, I don't know how many are in this picture, but in general, they have 50 ions in a single potential. And so they're able to get this all-to-all connectivity, but their gate fidelity is lower. And so even if these results are similar to the Quantinuum results, in general, the overall gate fidelity is a little bit lower. And so the question is why, and what is the optimal number? So what happens when you add ions to a potential? You get some positives, right? We've talked about this connectivity, which means that you can reduce the number of gates that you need to do. You don't need to do as many swappings. You don't have to do so much physical movement, which can reduce infidelities. And for certain things, you can get lower error correction thresholds, for instance, by using quantum LDPC codes. This is still maybe ongoing, but there's some promise for that at least. But there's also a lot of negatives. Negatives include reduced entanglement fidelity due to 2 coherent errors. So one is optical crosstalk errors, so just the fact that you need to pinpoint which 2 ions you want to entangle, and there might be some laser leakage onto your neighbor ions. And this is I'll be talking about a lot in this presentation. And the second is frequency crosstalk errors, which I'll also talk about in a second. You'll also have, as I mentioned before, more difficult optical engineering, both to do your gates, but also to detect the individual states of your ions. And you also start having correlated errors, either due to correlated local noisy fields, or also background gas collisions, which can ruin all the states of your ion string at the same time. And correlated errors are particularly bad for quantum error correction. Quantum error correction theorems hold under the assumption that all your errors are uncorrelated. But that assumption is not always true. And there's beginning to be thought about how to make error correction codes work also for correlated errors, but that is more nascent work. Okay. So yeah, I'll be talking today about trying to get this reduced entanglement fidelity to improve, and also how we can do some good optical engineering. Okay, so now let's talk about entanglement. And the first thing we have to do to talk about entanglement is talk about motional modes. So I said before that n ions have 3 n motional modes. These are all the motional modes for one radial direction for 5 ions. Okay, and any given mode is characterized by 2 things. It's characterized by its mode frequency and also its mode coupling vector. So the mode frequency determines where it will be on a frequency spectrum. So this is a spectrum in solid lines. It's for 5 ions. For dotted lines, we've added the extra 5 motional modes for 10 ions. So this is a spectrum that you'd expect to see from a string of calcium ions trapped in a potential, where we've said 0 megahertz is the electronic transition frequency. So this is the direct S to D transition. But for trapped ions, not only will you see this transition, but you'll also see what we call sidebands. So you'll see that the ion can, instead of just doing this 0 to 1 transition at this 0 megahertz frequency, we can also do a 0 to 1 transition, but also changing the motional mode from n equals 0 to n equals 1. So adding a quanta of motion. And that's what we call the blue sideband. So here, and we can decide which motional mode we'd like to add something to by tuning our laser frequency to each one of these modes. We can also coherently subtract 1 quanta of excitation from the harmonic oscillator by exciting the red sideband. So this takes you from 0 to the 1 state while subtracting 1 motional mode, or 1 motional mode quanta. Okay, so that's the mode frequency. Yeah. There are longitudinal modes. So this is just the radial modes. So there's 3 sets of modes. There's these ones, there's the ones that come out of the page that look kind of like this, and then there's the longitudinal modes as well. Yeah. And they'll have kind of, you can think of them similarly, one where they all move together, one where they smush apart. But you can control which set you excite by controlling where your laser, from what angle your laser is pointing. So your laser has to have some k-vector overlap with the motional modes that you're trying to excite. So you could see, by coming in at like a 45-degree angle, you could see all 15 modes for 5 ions if you wanted to. But you could also make sure that you can only excite 5 if you're careful with your alignment. So this mode coupling vector eta, so each mode M has an eta for each of the ions, and it characterizes the strength of the coupling of the laser to the motion, which, and in other words, it characterizes the amplitude of motion in that mode. So here, all the etas would be in the same direction. Right here, this middle ion would have an eta is equal to 0 because it doesn't move, and these would have equal amplitudes but opposite directions, opposite signs, et cetera, et cetera. Okay, so that's really quickly the motional modes of an ion chain. And even more quickly, how can we use them to mediate entanglement? So the way that we do it is we apply 2 frequencies, detuned from 1 motional mode. Okay, and this allows us to interfere all 4 possible ways that a transition could take place. So either starting in the 0, 0 state, we can excite the electronic state of 1 ion while removing a phonon, and then excite it again. Excite the other other electronic state while adding a phonon. That's this blue line. And there's 4 ways we can do that, right? Either we can do blue first and then red first, and then we can also do the same thing on the other ion. And when those 4 paths interfere, you get basically direct Rabi oscillations or direct oscillations between the 0, 0 state and the 1-1 state without populating this 0-1 state in the middle. So that's like a hand way to look at this and understand what's going on. Another way that we can think about it, different people find different things more intuitive, is thinking about a detuned push of a harmonic oscillator. So when we do a detuned push of a harmonic oscillator, we'll first speed it up and then we'll slow it down again. Right? And then if we have a quantum harmonic oscillator, a similar thing happens, and we drive a circular trajectory through phase space. So first we excite the motion and then we de-excite the motion. And this will only happen if we start either in the 0-0 state or the 1-1 state. So this allows us to put a state-dependent phase on our ions and create an entangled state with, as long as we can control this phase very correctly.
How do you add and subtract phonons? What's the mechanism do you use?
It's through the electronic state. So we have this really, really nice nonlinearity. So it's through these sideband transitions. So we can, yeah.
So it's like a fine, hyperfine structure or something.
Like kind of equivalent to that. Like your states, your spectrum will be broken up into just no change in phonons, or phonon, state plus 1 phonon, change your state plus change 1 phonon, change your state plus add 2 phonons. So that is eta squared, takes eta squared power. And you can also subtract phonons that way. So we get this direct nonlinearity through the electronic state.
And you control that by the electric field or
the optical field. Yeah, so this is like an optical spectrum. So this is all at 729 nanometers. This is all kind of around that direct, 411 terahertz frequency. But when we see like megahertz level sidebands. Yeah, an AOM. Exactly. Yeah. So if we can get direct frequency control, the kilohertz scale, which is possible with electronics, then we can do coherent manipulation. Yeah.
So the 2-pulse Balmer-Sorensen the drives are coherent?
The drives are, phase coherent. Yes.
Right, so in one of your previous slides, you had mentioned that the 2-qubit gate, the best ones have been 13 microseconds, whereas typically you get 100 microseconds, like of the order. I was wondering where that additional 70 microseconds came from. Is there like a relaxation time that you have to add in between?
Like I said, 30 microseconds for the best and 100 microseconds for what we're hoping to do?
Yeah, because if it's optical transitions, is it just the Rabi rate that governs your gate times?
Yeah. There's the Rabi rate, so you can always just use more power, but that often gives you technical problems. I will say that the gate with the highest fidelity actually did not use a Balmer-Sorensen gate. They used like a different gate. No, it's kind of like a light shift gate, but in the optical regime, they called it the optical, I always forget what it's called, OTDF. But they do, it's again like you get something similar to this, but actually you put phase on all 4 states, and then you balance your phases right so that everything works out. So you get a similar gate reaction. It's actually in the sigma z basis, but this is in the this is in a controllable basis, but yeah. They still use emotional modes, just the exact dynamics are slightly different. Okay, so when we're running this gate, we, have to pick some time t, which is equal to 1 over the detuning, so 1 over this detuning here, to make sure that we come back to the origin and start off with the same, and end up with a state where the electronic excitation is disentangled from the motional excitation. So that's one thing if we want to get a high fidelity gate. And then the second thing is we need to pick our power so that this trajectory encloses the right amount of area so we can get the phase phi that we desire. But if we can do that, we can make any arbitrary gate. Okay. The error sources are, of course, the normal incoherent error sources, magnetic field noise, laser amplitude and phase noise, and then also trap frequency instability. So if these frequencies are moving back and forth, then you can imagine that you can't drive them super coherently, and that leads to an error. But we also have these coherent errors. One is excitation of motional modes, which you can see pretty clearly from this image here, right? I've drawn this big fat arrow. We have better accuracy than this arrow suggests. But you can imagine that if you want to detune here, you're close to this mode, but you're also kind of close to that mode. And so even here, you're detuned from this mode, but you also have some detuning from that mode. And you don't drive it very much, but you drive it a little bit, and that might give you some errors. And that's the type of thing that you can model. And quite a lot of work has been done and also demonstrated to show that even with frequency crosstalk, you can get really high fidelity gates. It becomes kind of like an optimal control problem. You have all these trajectories that you want to close, so you have some final state that you want to get to, and your parameters that you can control are the amplitude of your laser beam, the frequency of your laser beam, and the phase of your laser beam. And you can change all of those at every time step to create whatever trajectories you want to make sure that all of your modes close and you get exactly what you want. And this has been demonstrated a lot. There's another problem, though, which is that you can excite multiple ions. And this is what we call optical crosstalk. It has been significantly less studied and is what I'd like to talk about today. So optical crosstalk. Here's a picture of 5 ions, and we're trying to do an entangling gate between ions 2 and 4. And so I have 2 Gaussian laser beams, excited those 2 ions. This is, for a 1 megahertz axial trap frequency. The axial trap frequency determines the actual spacing of the ions. And with a beam waist of 2.2 microns, which is not incredible for 729 nanometers, but it's definitely a respectable beam waist to ask your graduate students to create in the lab. Especially because this all has to be super stable, right? And so for 5 ions, it actually looks quite all right. We'll see in a second that there is still some optical crosstalk, but not so much. But as we add ions into our trap, if we keep the same axial trapping frequency, the spacing between the ions decreases. So this is the same exact trap. We've just added more ions. And you can see for 15 ions, there's basically 100% crosstalk between the middle ion. So if you're trying to do an entangling gate between these 2 ions, then the ion in the middle will also get entangled, right? And so this is a clear demonstration of why it's not always easy to just add ions into your trap. We can also quantify this a little bit better. And here, so if you're trying to pick out the 2 ions that are around your center ion for a different number of ions in your chain at a 1 megahertz trapping frequency for 3 different beam wastes, what you expect your intensity at the center ion to be. So you can see, and we want to get to about 10 to the minus 4 error. That's the best gates that we have more or less. And so we don't want this to be a limiting error. And you can see that even with this 0.44 microns is about a 0.6 NA, which is quite good. We still can't go beyond about 50 ions without doing something fancier. And then I would also just caution that even if you could get 500 nanometer beam size, that would also mean that your beam pointing stability would also have to be that good, right? So it's not always better to just decrease your beam size infinitely. And then, also, we were talking, this is only about pure Gaussian beams with no aberrations, which of course never happens. And this will only become worse when we really start integrating optics and scaling these optics. So there's a lot of work to be done here. So what can we do? So the phase that we accrue for some particular time or some particular power is proportional to the electric field at each ion, the single ion Rabi frequencies at each ion. So that's omega 1 and omega 2. And as we said, this is set by the optical setup. But we also have 2 other parameters, which is eta 1 and eta 2. And that depends on the motional mode. So it's a very naive thing that you could try, which is just pick some mode where the eta targets, or the eta of your target ions, is much larger than any eta of your neighboring ions. So for instance, for this 4-ion string, if we wanted to entangle ions 1 and 4, This is the mode that most people would use. So this is the high frequency or the high spatial frequency mode. People use this for a technical reason that most noise is common mode. Most electric field noise, which causes decoherence of your motional mode, is large length scales, and so it doesn't really excite this motion because you'd have to have opposite polarity electric fields at each of these ions to excite this motion, and the chance of having that on the micron scale when your electrodes are hundreds of microns away is pretty low. So people like to use this motional mode, but here, even with this fairly good optical isolation, you still would only be limited to a fidelity of 96%, which is respectable, but not great. But if you choose this mode, you can get 2 nines of fidelity. And you can see that by looking at the, so here, this shows the the gate speed between each pair of ions. Here you have these extra gates, and that's because this ion here has such a high coupling to the motional mode, right? So it really makes the situation worse, whereas here, all these extraneous gates, you can't even really see them. They're very low. And so that's the general idea. And Vikram Keshup, who's a research assistant in the group, came up with a really nice analytical model to take into account all of these coherent errors. So for incoherent errors, it can be, in general, hard to do a full simulation for lots of ions with large motional modes. But for coherent errors, you can find very nice analytical solutions for the errors that you expect, allowing us to do a full modeling and see what this looks like for all of the ion pairs in a 5-ion chain or more ion chain. So this shows the expected fidelity or expected error in fidelity. We like lighter colors on this plot for each of the ion entanglement pairs in a 5-ion chain for each of the modes. So mode 0 through the common mode. And this here shows the best that we can hope to get and which mode we should use to get it for each given pair. And because all that we need to do to pick the motional mode is just change the frequency of our laser by a megahertz or so, this is experimentally fairly straightforward. So we're very excited because our setup is not quite there yet. But we are working with Sandia and their QScout platform, which is a testbed platform with 5 ions that is actually their entanglement fidelity is limited by their optical crosstalk. And so we hope to show that this helps them and improve their gate fidelity. So stay tuned for some results, some experimental results. Yeah, this is for these gates, about 100 microseconds. Yeah. And there's many different error sources, but yeah, they believe that at least some of their gates are limited by optical crosstalk.
And then you're showing this atoms moving up and down. How many nanometers or microns are we talking about?
Oh, very few. So we work very close to the ground state. The ground state motion for a ion at a 1 megahertz calcium ion at a 1 megahertz trapping frequency is something like 10 nanometers, and we only work on a few phonon or even just partial phonon excitations. So very 10 to 20 nanometers, and you could excite it more. There's something called the Lambdicker regime, where we would like the motion to be much smaller than the wavelength of light, and we try to stay within that regime. So yeah, we want it to be on the order of tens of nanometers. Perfect. So yeah, now I'd like to talk briefly about optical engineering. There's no more questions about that. Okay, so optics for ion traps. There's 3 parts. We need a really good source. We need 4 of them, right? 4 different wavelengths. We're also, if we think about 10 to the 8th ions, we'll need a lot of power. So our single and 2 qubit gates for calcium can be run with kind of 10 microwatts of power, of course, depending on your focusing size and many other things. But we're talking about tens of microwatts. But still, tens of microwatts over even just 1 million ions is 10 watts. So you don't probably want to start with a 10-watt laser and move it to all of your different ions. It'd be nice to have some integrated laser source sources, so you could, or at least some integrated tapered amplifiers or integrated amplifiers in general. So you could just distribute a seed laser that was amplified at your different modules. I won't really be talking about that today. The second thing that you need is modulation, so you need to be able to control the amplitude, frequency, and the phase of your signal. And the third thing is that you need to route your light and then focus it onto your ions. So first for this modulation, our requirements here is that you need megahertz switching speeds. You need 40 dB on-off isolation. So when we don't want to excite our ions, we need, the hand wavy thing is we want 10 to the minus 4 errors, which suggests we want about 40 dB of optical isolation. But the more, the better. And then you also need about 40 dB of optical amplitude and phase stability. So, I'm sure many people have heard similar talks like this, but what we do now is we use AOMs, so bulk acoustic optic modulators. These are easy, they have high quality beam shape. This is one compact setup that has, I think actually this is for 2 channels, and we were really proud about this because it's actually really compact. It's probably not actually so far different from the actual size on the screen. But yeah, this is 2 channels. And so they're pretty bulky, and they also require a large power. So each of these acoustic optic modulators takes about 1 watt. And of course, they're hard to align, or at least they're somewhat painful, and they're not flexible. So you can ask somebody to create 1 or 2 or maybe 10 of these if you're really nice, but not 100. So we're moving towards integrated photonics, which are compact, fast, and stable, but of course they add complexity, and it's still unknown if they meet specifications because active visible photonics are still really at the cutting edge. So this is a picture of a lithium niobate active photonic chip made at MIT, which has 256 channels, and this is the size of a penny, and now I've copied the same image here to scale, and it's very small. So what we are doing is the first chamber that we're building is a chamber that is a pretty standard trap. So it's just one of these quadrupole traps. It's not scalable in any sense of the term, but what it is stable, and there are no wheels being reinvented. This will allow us to trap tens of ions fairly stably. We then have some big imaging optics and then we'll be able to test different photonic integrated circuits and rearrange their outputs using a spatial light modulator and image them onto our ions. And this is going to be our method as a little test bed for people who are making new integrated photonic devices to be able to test them directly on ions without having to build ion systems themselves and without us having to rip apart trapped ion setups. And trapped ion setups take a long time to build, so no one wants to rip them apart. And I guess I didn't actually write this on this slide, but this is a chip that we have now that was made in the group of Matt Eichenfeld, who I guess is not here today, with this aluminum nitride, silicon nitride on aluminum nitride platform that provides these near gigahertz switching speeds, which is more than enough for us. And there have been some demonstrations that show towards this number of isolation, and you can always cascade them. And then there's also the question of amplitude and phase stability. Actually, a big question is if the spatial light modulator will be able to give us the phase stability that we need. And so we have some work ongoing at the moment to really, even before we get ions, test the full amplitude and phase stability of the full system to give us an understanding of what we will expect on our ions. Because really any measurement that you can do classically is better than trying to do it on the ions themselves, because those measurements are time intensive. And then the last thing that we should talk about is routing and focusing of the light. So again, our requirements here is that you get 40 dB ion-ion isolation. So when we want to excite one ion, we're not exciting the other. Again, as I said, we can kind of get around that a little bit, but we want to start as good as possible. We need multi-wavelength operation. So on every ion, we need these 4 lasers. There are many reasons that you'd want to just detect one. So we'd like to, There's maybe schemes where some of these could excite all the ions at once, but at least they all need to be on the ions at the same time. And in the end, we'll need centimeter scale field of view, right? If we really want 1 million or more ions, that's going to take centimeters of space. And if we want to be able to excite them all at the same time, we need to be able to have that field of view.
So this is not the modular architecture.
It's still the modular architecture, but now we're thinking about, like, once we have lots of modules. And also, but it's still, we need to take into account what each module will look like, because that will kind of depend how many beams we're going to make with these focusing optics. But it's still modular. It's just, yeah, now we're talking about what happens when we have lots of modules.
And then when you have lots of modules, you need also optics to show. You need to show
Electric. Yeah. Mm-hmm. And that has been shown fairly extensively. So let's say to first order, it's a solved problem. There's still open problems, but it's fairly, Honeywell has done an incredible amount of work figuring out how to do that shuttling as best as possible. Okay. So yeah, as I said before, this Quantinuum or Honeywell, they use these beams that go across the surface of their trap. And this really just gives 1D, it allows you to only do 1D lines, right? Because then your beams are going to intersect with your other ions if you try to tile it in 2D. And actually, really, most work works in this 1D plane. You come in with your lasers. Because we're working with these surface traps, it's really hard to come in from the top in general. So I would say Sandia has a trap that they call the high optical axis trap that has a slit in it, but they tell you not to use that slit. So, for better or for worse. But our goal is to really push this forward, and we have some ideas of some reasons why our approach should work. So our goal is to open up our excitation options and enable individual addressing on a large ion string, and this finally allow us to do tiling in 2 dimensions. So the main goal here is to trap ions over gaps in electrodes, and we'll see how we're going to do that. So, and not only are we going to trap over gaps in electrodes, but so currently we can have these optical systems that give a high numerical aperture, but a very low field of view. And so instead we're going to have focusing optics at every site. So we can gain the advantages of both large field of view while maintaining the high numerical aperture. So if we have lenses exactly where we need them, only 100 microns or hundreds of microns from our ion, that will allow us to get the best of both worlds, hopefully. And the way that we're going to do that is with two things. The first is that we're going to fabricate undercut electrodes, and this is going to give us this high numerical aperture access. So in my postdoc, we used a cool platform with doped silicon electrodes. Doped silicon electrodes are nice because they allow us to do backside routing. So this is a circularly cylindrical trap that we use to control the rotational degree of freedom of 2 ions. And one thing that you'll notice in this picture, that there's no traces coming out from the electrodes, which would be horrible for this application because we wouldn't be able to get these center electrodes, right? You'd have to have some big wire going across there, and that would ruin the electric fields. So the thing that enabled this was using doped silicon and being able to do backside routing of the electrodes. Another thing is that doped silicon, it has a crystalline surface, and I didn't talk about this at all, but one of the big problems in trapped ion quantum computing is electric fields from surfaces, and no one knows where they come from, so we call them anomalous heating. But one option is that it comes from just metals that are crappily, they have some topology, and electrons get trapped in them, and then when you put a DC or RF field over them, they move around. And one possibility, I think pretty reasonable thing to assume is that if you had a very crystalline surface, you could control that topology very well and maybe get less electric field noise. And this is somewhat borne out. No real experiments have been done, but I would say that this trap, where we didn't try at all to get low noise, had, if you plot all of the heating rates on every trap that has ever been used for trapping ions, this heating rate is at the very bottom of that. So it's not like crazily lower, but it is definitely low. And again, we didn't try very hard to make it low, so we could try harder. And the fabrication is straightforward. You just need to do silicon fab, and these, this is 1 millimeter, so this is all optical lithography. Yeah. And then we'd like to combine this with some fabrication that I did during my Ph.D., where we built freestanding all diamond structures to create some freestanding all doped silicon structures. So just, because I like this SEM, I'll belabor it a little bit. Everything that you see here is diamond. This is 50 microns of just diamond that is attached by 50 nanometers, little pegs here. And with this undercut that we developed, we were able to carve these diamond structures out. So we want to do the same with silicon, with the very simple idea that if we just etch down, you have very low numerical aperture. But if you do these undercuts, it brings your numerical aperture up significantly, while still allowing you to have the electrodes that are near your ion fairly close together. And one might ask, why don't you just bring this up here? It would be a good question. But again, this anomalous noise, it's even worse when you have dielectric, so we want to keep all weird materials as far away from our ion as possible. So this allows us to keep our materials pretty far away from our ion, but still get this high numerical aperture. And then at the bottom, we can, lithographically define focusing optics. Yeah, so we can flip it over and define, here I've something that could be like a meta surface. You could have a real optic there, anything that you like. And so, we're pursuing focusing meta surfaces in collaboration with Arka Majumdar, also at the University of Washington. And what's nice about this is it's lithographically aligned, right? You make this, and then you can align these optics directly to your trapping electrodes, and that's the hope.
What's the spatial scale?
Yeah. So this is 250 microns, and this is also, depending exactly what this undercut is like, 100 to 200 microns. And then the metasurface, that's a metasurface question, but they're on below the wavelength of light, so tens of nanometers. Yeah. So there has been this is a great question. I'm glad you asked it. So there has been a little bit of work done with waveguides integrated directly with the trapping electrodes. So you have waveguides and then gratings, exactly as you said, up and move up to the ions. The problem with that is that they are fixed in fabrication. And so there actually hasn't been a demonstration where they're able to get multi-wavelengths all at the same position. There's been one demonstration that kind of shows that, but they actually kind of cheat and move the ion around to get all the different lasers. So they have 4 different wavelengths, but they're all pointing in different directions. And so they can move it over here, and they move it over there, and they move it over here, and they move it back. It's still a tour de force, and I don't want to minimize it. But it's not clear how this will work. The other thing is that if we want lots of ions in the same trap, you can imagine for these waveguides, you're coming in with one channel into one grating coupler. And this grating coupler, if you want to get single ion addressing, you still need this numerical aperture. You're constrained by geometry. And so that means the size of your focusing optic is much larger than your ion-ion distance. So it's then your optics that define how many ions can go in each module. And that is usually like defined as 2. Just because you just always do global addressing. Which it seems, again, like a handcuffing of the ion system. And so here, the trick is that we're coming, I see no inherent reason that we need to put everything together on the same chip. So here we're coming in with free space light, and that free space light, as I said, might come from a different integrated photonic chip, but you have some mode-changing optics in the middle that allows you to just think of this as a normal lens. You can, with the same bulk structure, address different ions by changing your input angle slightly. Right, so you change your input angle slightly, that addresses a different ion, but you're still using the same optic. And I think that's the why we're going with this solution and not the waveguide integrated, with waveguides integrated directly with our trapping electrodes. Yeah, glad, yeah.
System.
Yeah.
And then you can shine with a laser beam 2 of them, but depending on the polarization, you can focus it for one and not the other.
Yeah, definitely. And then you can also exploit the you can create metasurfaces that have the same focus for all the 4 wavelengths of light. So maybe we want to have different metasurfaces for our qubit excitation, which is like very particular, but we could, at least for the 3 wavelengths that do the global addressing, the dipole transitions, 397, 854, and 866, we could have one meta-optic that focuses all 3 of those onto the same location, which is really hard to do in a grating coupler.
So this is silicon, right?
The electrodes are silicon, yeah.
But the material itself is not.
This material would be oxide, and then maybe put this in the nitride or something, some metasurface thing. There are many ways that one could think to do it. Yeah. Okay. And and so just as I was sent this SEM yesterday, so I wanted to be able to show it. So now we have in our clean room the ability to do these undercuts. So this is just a test structure. It's not a trap, but we can create these undercuts. And actually what's kind of nice about it is that the degree of the undercut is determined by the size of the slit. So we can say that, okay, the places where we don't want undercuts, we just have 10 micron slits there and there won't be very much undercut. And then where we have this big aperture, we'll kind of automatically get more undercut, which is exactly what we want. This is the same, it's isotropic, it's the same. So SCREAM, there's a process called SCREAM that I never remember what it stands for, but it's a MEMS process. And we're basically following that. And this was the inspiration for the diamond work. So they're going full circle.
So it seems that the depth is dependent on the aperture.
Yeah, so what we did here is we etched down first. So we do a first etch down. So this is not a final structure. In a final structure, we'd etch all the way down and then etch. But yeah, we etch down, coat everything, etch down again, and then this is this undercut. And you can imagine if we didn't etch here, it's kind of etching isotropically. So just as it etches out more, it also etches down more. Yeah. Yeah. So that was very exciting. So now we can do this with real traps and hopefully flip them over and make some metasurfaces and really show that we can get this full chip scale excitation of ions. Okay, and with that, I'd like to conclude. So I talked about how we can reduce coherent optical crosstalk errors, how we can do optical engineering to scale control. Some things I didn't talk about, but I'll just mention really quickly if anyone has any questions about them. We are doing work to model and reduce the effect of background gas collisions. This is an error that in trapped ion systems is really swept under the rug, and people don't like to talk about it because the collision rate is kind of at the same order of, it's like slower than the experimental rate. So you can just throw out the experiments where there happened to be a collision at this point in time. But that rate is still on the order of 1 per 10 to 100 milliseconds, depending on how good your vacuum is, right? And so if we're really thinking about a fully fault-tolerant quantum machine that's running for days, probably, this will become an error that we have to care about. And the work that's been done on this, there have been like a few measurements of background collision rates or reorder rates, and the data don't make so much sense. So we have both modeling work, and also these experiments are fairly easy to set up, so they're a good first experiment to do when we get our system up and running. We also have ideas about how to further extend the work that I talked about today to not only be stuck with the motional mode vectors that harmonic oscillators give us, but actually tailor the motional mode spectrum and these coupling vectors using either electric forces, so non-harmonic potentials, or optical forces. And optical forces would be particularly nice because they would allow us for very fast control, because you can turn these fields on and off, optical fields on and off really quickly, and also tighten them to wavelength scale, to localize them to wavelength scale. And then finally, so, I've talked very much about the bottom-up idea of how do you build a quantum computer, so really starting from the qubit level errors, but there's also the question coming from the top down, right? So I have some application or error correction that I want to run. How should I allocate my resources, right? And right now there's a lot of computer scientists and theory people thinking about that, and a lot of people like me thinking about the bottom, but we want to try to bridge that gap and be able to build a model of our system that allows the more theory people to take a physics-driven approach to optimal resource allocation. And with that, I'm happy to take any questions.